What if data had a shape? Think about it for a moment. We often imagine data as a vast shapeless sea of numbers. It's a spreadsheet with endless rows and columns. It's a stream of ones and zeros flowing through the digital ether. But what if, hidden within that chaos, there was a structure, a form, a secret geometry that could tell us something profound about the world we are trying to understand? This is not science fiction. It is the core idea behind a branch of mathematics that is quietly revolutionizing our digital world. It's a field that allows us to find meaning not just in the quantity of our data, but in its underlying shape, revealing connections that were previously invisible to us. This might sound abstract, but the principle is surprisingly intuitive. Imagine you are trying to navigate a new city. You could have a list of every single street address, a massive and overwhelming collection of data points, or you could have a map. The map doesn't show you every single detail, but it reveals the city's structure. It shows you how roads connect, where the major districts are, and how to get from one point to another. The map gives the data shape. This is precisely what mathematicians and computer scientists are now doing with information, turning messy, high-dimensional data sets into coherent, understandable shapes that guide our decisions and discoveries in powerful new ways. The power of this approach lies in its ability to see the big picture. In an age where we are drowning in information, a new kind of literacy is required. We need methods that can filter out the noise and highlight the essential structure. For instance, think about the data from millions of online shoppers. We could get lost in the individual purchases. Or we could look for the shape of their collective behavior. Are there distinct clusters of customers? Are there loops of activity that show people returning to certain products? Finding these patterns is like finding the main highways and neighborhoods on our city map. It gives us a framework for understanding a complex system. This is where topology enters the scene. Topology is often called rubber sheet geometry. It's a field of mathematics that studies the properties of shapes that are preserved when you stretch, bend, or twist them, as long as you don't tear or glue them. To a topologist, a coffee mug and a donut are the same object because they both have exactly one hole. This might seem like a strange or even playful observation, but this focus on fundamental connectivity is exactly what makes topology so powerful. It helps us ignore the minor details, the noise, and focus on the essential, enduring structure of our data, unlocking secrets that traditional statistics might miss. The idea that a coffee cup is the same as a donut is more than just a mathematical party trick. It represents a fundamental shift in perspective. It's about moving beyond precise measurements and rigid forms to understand something more essential: relationships and connections. In the world of computer science, this way of thinking is a game changer. Computers are incredibly good at crunching numbers, but they often struggle to grasp context or see the overarching pattern. Topology provides them with a new kind of vision, one that is less about counting and more about connecting the dots in a meaningful way. It's a tool for finding the forest, not just cataloging the individual trees. Consider how this applies to a real world problem, like understanding a social network. You could analyze it with traditional metrics, counting the number of users, likes, and shares. This gives you a lot of numbers, but might not tell you much about the community's health or structure. Using topology, however, you could map the shape of the connections. You might find dense clusters of friends, identify key influencers who bridge different groups, or even spot isolated communities. You might see holes in the network, indicating a lack of connection between certain groups. This qualitative, shape-based insight is often far more valuable for understanding how information flows and how communities evolve. This new lens is especially crucial in fields dealing with incredibly complex and high-dimensional data. Think about genetics, where scientists analyze thousands of genes across thousands of patients, or neuroscience, where researchers map the firing patterns of millions of neurons. In these scenarios, the data exists in a space with so many dimensions that we can't possibly visualize it directly. It's like having a map with 1,000 different directions for every single point. Topology gives us a way to project this impossibly complex shape down into something simpler and more interpretable, like a 2-dimensional or 3-dimensional model that preserves the most important structural features of the original data. Ultimately, topology's role in computer science is about providing a language for structure. It is helping us build smarter algorithms for machine learning, design more resilient networks, and even accelerate the discovery of new medicines by understanding the shapes of molecules. It's a powerful reminder that sometimes the most profound insights come not from measuring things more precisely, but from seeing their underlying connections in a completely new light. The shape of data is not just a metaphor. It is a tangible, computable property that is unlocking the next wave of technological innovation and scientific discovery. At its heart, topology is the study of properties of space that are preserved under continuous deformations. This sounds complicated, but the core idea is wonderfully simple and visual. Imagine you have an object made of an infinitely stretchy and flexible material like a rubber sheet. Topology is the branch of geometry that explores what properties of that object remain unchanged, no matter how much you bend, twist, stretch, or compress it. The one strict rule is that you are not allowed to tear the material or glue separate parts together. This is why topology is often playfully called rubber sheet geometry. It's less concerned with rigid measurements like length, angles, or straightness, and far more interested in the fundamental nature of connectivity and continuity. Think of it this way. To a classical geometer, a small circle and a large circle are different. Their radii are different, and their circumferences are different. A square and a circle are fundamentally distinct shapes. But to a topologist, they can all be the same. You can take a square drawn on a rubber sheet and smoothly deform it into a circle without any cutting or pasting. You can stretch a small circle into a larger one. From a topological viewpoint, these objects are equivalent because one can be transformed into the other through this continuous process. This focus on abstract, preserved properties is what makes topology so different from the geometry we learn in school. And it unlocks a powerful way of classifying shapes based on their most essential features. This process of continuous transformation is known as a homomorphism. It's a fancy word for a simple concept. Two objects are topologically equivalent if there is a continuous two-way mapping between them. It's like creating a perfect, flexible bridge between every point on the first object and every point on the second without ever breaking the connection. This means that a hollow sphere, a cube, and even a lumpy potato shape are all topologically the same. You can imagine inflating a deflated rubber ball, a sphere, into a cube shape, or squishing it into a potato-like form. The essence of its spheeriness, its single continuous surface without any holes, remains intact throughout these transformations. Why is this stretchy perspective so useful? Because it teaches us to ignore irrelevant details and focus on what truly matters about an object's structure. In the real world, and especially in the world of data, things are rarely perfect. A handwritten number 8 might be drawn sloppily with one loop larger than the other. A traditional algorithm might struggle to recognize it, but a topological approach sees its fundamental structure, 2 connected loops. It doesn't care about the wobbly lines or imperfect circles. It sees the essential 8ness that survives the deformation. This ability to see past the noise and identify core structure is precisely what makes topology a revolutionary tool in modern computer science. If topology is all about transformation, how do we tell 2 objects apart? If we can stretch and bend things so freely, what stops us from saying everything is the same? The answer lies in the concept of topological invariance. These are specific properties of a shape that do not change no matter how much you deform it through a homeomorphism. They are the fundamental truths of a shape that survive the stretching and bending. If 2 objects have a different topological invariant, then you can be absolutely certain that one cannot be transformed into the other without tearing or gluing. These invariants act as the unique fingerprints for different topological classes of objects. The most famous and intuitive invariant is the number of holes. Consider a flat rubber disc. You can stretch it into an oval, a rectangle, or any other blob-like shape, but no amount of continuous deformation will ever create a hole in it. To make a hole, you would have to puncture the material, which is a form of tearing, an illegal move in topology. Similarly, if you start with a washer, which is a disc with one hole in it, you can never get rid of that hole by just stretching or bending. You would have to fill it in, which is equivalent to gluing a patch over it. This simple count of holes is a powerful way to distinguish between fundamental types of shapes. This idea extends far beyond simple holes. Another crucial invariant is the number of connected components. Imagine you have 2 separate rubber balls. They constitute a single topological object with 2 distinct pieces. You can stretch each ball individually, move them closer together or further apart, but you can never merge them into one continuous object without gluing them. The property of having 2 pieces is an invariant. This is incredibly useful in data analysis. For example, if a data set forms 2 separate, distinct clusters, this is a topological feature. It tells us there are likely 2 different groups or phenomena at play, and this structural information is preserved even if the data is noisy or distorted. These invariants, like the number of holes, connected components, or more advanced concepts like Euler characteristics and Betti numbers, form the bedrock of topological analysis. They provide a quantitative way to describe the qualitative features of a shape. When we analyze data using topology, we are essentially trying to compute these invariants. We are asking, what is the fundamental, unchanging structure of this data set? How many classes does it have? Does it contain significant loops or voids? By answering these questions, we can build a simplified yet profoundly insightful skeleton of our data, giving us a map to navigate its complexity without getting lost in the noisy details of precise measurements. The most iconic example in all of topology is the equivalence of a donut and a coffee cup. At first glance, this seems, well, kind of absurd. A donut is a sweet, ring-shaped pastry. A coffee cup is a ceramic vessel with a handle, designed for drinking. They have different functions, are made of different materials, and have completely different geometric properties like curvature and volume. Yet in the world of topology, they are surprisingly indistinguishable. This is because they share the same fundamental topological invariant. They both have exactly one hole. This single powerful observation perfectly encapsulates the topological way of thinking, looking past superficial differences to find a deeper structural similarity. Let's try to visualize the transformation. Imagine the coffee cup is made of soft, pliable clay. You can start by squishing the main cup part down, shrinking it into a thicker, more compact base. The handle remains. Now, you can fatten up that base and simultaneously widen the handle's opening. As you continue to mold the clay, the part that was once the cup becomes the main body of the donut, while the handle remains the hole through the center. The hole in the coffee cup's handle has been continuously deformed to become the hole in the center of the donut. At no point did we need to tear the clay or glue new pieces on. We have demonstrated a homeomorphism between the two. This isn't just a clever party trick. It reveals the power of abstraction. By declaring the donut and coffee cup to be the same, topology gives us a new classification system. It groups objects not by how they look or what they measure, but by their connectivity structure. A wedding ring, a rubber band, and a polo mint are all, topologically speaking, in the same family as the donut and the coffee cup. They are all examples of a torus. In contrast, a sphere, like a basketball, is fundamentally different because it has 0 holes. A pretzel with its 3 holes is in another category entirely. This classification scheme is incredibly robust because it is immune to noise and deformation. This principle has honestly profound implications for computer science and data analysis. Imagine you are trying to teach a computer to recognize different objects. If you rely on traditional geometry, you'd need to account for every possible variation in size, orientation, and minor imperfections. But if you teach it to identify topological invariance, it can recognize the one-holedness of a coffee cup, regardless of its specific shape or style. This is key to building more robust pattern recognition systems. The donut and the coffee cup are therefore not just a fun example. They are a deep metaphor for how topology helps us find the stable, essential features in a world of messy, ever-changing data. We live in an era of unprecedented data collection. Every click, every purchase, every medical scan, and every social media interaction generates a stream of information. We are creating data at a rate that is almost impossible to comprehend. We often think of this as a good thing, and in many ways, it is. More data should mean more knowledge, but there's a catch. Having more data doesn't automatically lead to better understanding. In fact, without the right tools, it can lead to the opposite. Confusion. We find ourselves drowning in a vast ocean of numbers, desperately thirsty for meaning. This is where the concept of shape becomes not just an academic curiosity, but a practical necessity for survival. Traditional methods of data analysis often focus on summary statistics. We calculate averages, medians, and standard deviations. These are useful, but they can be deeply misleading. They boil down complex realities into single numbers, stripping away all the nuance, and most importantly, all the structure. A famous example is Anscombe's quartet, a set of 4 data sets that have nearly identical statistical properties, but look completely different when you plot them on a graph. One is a simple line, another a curve, and 2 others show distinct patterns. This proves a vital point. Numbers alone are not enough. The shape of the data tells a story that the statistics completely miss. Thinking about data in terms of its shape forces us to ask different kinds of questions. Instead of asking, what is the average value? We start to ask, what is the underlying structure? Are there distinct groups or clusters within the data? Are there loops or cycles that indicate recurring behaviors? Are there unexpected holes or voids where we would expect to see data points? These are questions about connectivity, relationships, and global patterns. They are fundamentally topological questions. By looking for shape, we move from being simple accountants of data to being architects of understanding, building a coherent picture from the raw materials of information. This shift in perspective is critical because the real world is full of complex interconnected systems. The economy is not just a list of transactions. It's a web of relationships. A disease is not just a collection of symptoms. It's a process that unfolds within the intricate network of the human body. To make sense of these systems, we need to see their shape. We need methods that can capture the intricate dance of connections that defines them. Simply counting the data points is like trying to understand a city by counting its bricks. To truly understand it, you need a map. You need to see its shape. There is a classic saying that warns us against missing the forest for the trees. This proverb perfectly captures the central challenge of modern data analysis. The trees are the individual data points, each one a specific measurement, a single transaction, or a pixel in an image. They are important, of course, but if we focus on them too closely, we can lose sight of the bigger picture. The forest is the overall structure, the emergent pattern that arises from the collective arrangement of all those trees. It's the shape of the system as a whole. Topology is the mathematical tool that gives us the ability to zoom out and finally see the forest. Imagine you are a biologist studying a flock of birds. You could attach a tracker to every single bird and record its precise location second by second. You would end up with a gigantic data set of coordinates. Analyzing each bird's path individually would be overwhelming and might not reveal much about the flock's behavior. But if you look at the shape of the data from the entire flock, you might see something amazing. You might see them moving together in a coordinated donut-like ring, a torus shape, to evade a predator. This shape is a property of the group, not of any single bird. It's the forest, not the trees. And it tells you something profound about their collective strategy. This ability to find global structure is what makes topology so powerful. It helps us find patterns that are robust and meaningful. In many real-world scenarios, individual data points can be noisy or unreliable. A sensor might give a faulty reading, or a customer might make an unusual one-off purchase. If we focus too much on these individual trees, we might be led astray. Topology, with its stretchy perspective, is naturally designed to ignore small-scale noise. It doesn't care about the exact position of each tree. It cares about how the forest is connected, whether it's one continuous wood or several separate groves. This makes it an incredibly resilient tool for finding truth in messy, imperfect data. Ultimately, seeing the forest is about finding simplicity in complexity. Massive data sets are, by their nature, overwhelmingly complex. Our brains are not equipped to make sense of thousands of variables at once. Topological data analysis, TDA, acts as a kind of translator. It takes this high-dimensional, impossibly complex information and projects it down into a simplified structural summary, a topological signature. This summary, often visualized as a graph or a diagram, is the map of the forest. It allows us, as human beings, to use our powerful pattern recognition abilities to grasp the essential nature of the data and make informed decisions based on its true underlying shape. One of the biggest challenges in modern data science is the curse of dimensionality. This sounds intimidating, but the idea is fairly straightforward. We're used to thinking about the world in 3 dimensions: length, width, and height. A graph on a piece of paper has 2 dimensions. But what about a data set that describes a person's health? You might have columns for age, weight, height, blood pressure, cholesterol level, heart rate, and honestly, hundreds of different genetic markers. Each of these columns is a dimension. Suddenly, your data doesn't live in a simple 3-dimensional world. It lives in a space with hundreds or even thousands of dimensions. Visualizing such a space is, well, impossible for the human mind. Our geometric intuition, built on a lifetime of experience in a 3-dimensional world, completely breaks down. In high-dimensional spaces, things behave in very strange ways. The concept of distance becomes less meaningful, and almost all the data points tend to end up far away from each other, near the edge of the space. This makes traditional methods like clustering, which rely on our intuitive understanding of closeness, much less effective. Trying to find patterns in this environment is like trying to navigate a city where every location has 1,000 different coordinates, and the map is a tangled mess. This is where topology provides a lifeline. Because topology is not concerned with rigid distances or angles, it is uniquely suited to explore these bizarre high-dimensional worlds. It doesn't care that the space is stretched out in strange ways. It only cares about connectivity. Topological data analysis gives us a systematic way to probe these high-dimensional point clouds and ask fundamental questions about their shape. Are all the points in one big clump? Or have they separated into multiple pieces? Are there any loops or voids that might represent cyclic processes or missing data categories? It builds a scaffold based on connections, not on unreliable distance measurements. This process can be thought of as casting a shadow. Imagine you have a complex 3-dimensional object, like a chair. If you shine a light on it, it casts a 2-dimensional shadow on the wall. The shadow is a simplification, but it retains some of the essential structural information of the chair. TDA does something similar, but in a much more sophisticated way. It casts a shadow of the high-dimensional data cloud down into a low-dimensional representation, like a network graph that we can actually look at and interpret. This topological shadow preserves the most important connectivity features, like clusters and loops, allowing us to finally see the hidden shape of data that was previously lost in the fog of high-dimensional space. So, how do we actually find the shape hidden within a dataset? The primary tool that powers topological data analysis, or TDA, is a sophisticated technique called persistent homology. While the name might sound daunting, the core idea is quite intuitive. Think of it as a way of taking an X-ray of your data. A medical X-ray allows a doctor to see the underlying bone structure of a patient, looking past the skin and muscle. In the same way, persistent homology allows a data scientist to see the underlying topological skeleton of a data set, looking past the noise and the complexity of individual data points to reveal the fundamental clusters, loops, and voids that define its true shape. The process works by building a series of shapes on top of our data, which is usually represented as a cloud of points. Imagine each point in your dataset is an island in an ocean. We start to slowly grow a circular region around each island, and as we increase the radius of these circles, they begin to overlap and merge. When two circles overlap, they form a connected component. When three or more overlap in a ring, they might trap a region of empty space, forming a loop or a hole. Persistent homology carefully tracks when these topological features, the connected components, the loops, the voids, are born, and when they die, as we continue to expand our circles until everything has merged into one single mass. What makes this process so powerful is the persistence part. Some features that appear might be very short-lived. A small loop might form and then quickly get filled in as the circles continue to expand. This is likely just noise in the data. However, other features might be very persistent. A large, significant loop might be born at a certain radius and survive for a long time before it finally gets filled in. This persistence is a strong indicator that the feature is a genuine, meaningful part of the data structure, not just a random accident. It's like the difference between a fleeting shadow and a solid object. Persistence tells us what is real. By tracking the birth and death times of all these features, we can distinguish the signal from the noise. The most persistent features are the ones that define the true topological signature of the dataset. This gives us a multi-scale view of our data's structure, showing us which patterns exist and how significant they are. We are no longer just looking at a static cloud of points. We are observing a dynamic process that reveals the data's hidden architecture layer by layer. This X-ray vision is what allows TDA to provide such deep and reliable insights into the structure of complex information, turning a messy cloud into a clear and interpretable map. Once persistent homology has scanned our data and tracked the birth and death of its topological feature, how do we make sense of this information? The result is not a single, static picture, but a rich, multi-layered summary of the data's shape at all scales. One of the most elegant and intuitive ways to visualize this summary is through something called a persistence barcode. Each feature that was detected in the data, each connected component, each loop, each void is represented by a single horizontal bar. The bar starts at the moment the feature was born and ends at the moment it died. The length of the bar, therefore, directly represents its persistence. Imagine looking at one of these barcode charts. You would see a collection of horizontal lines of varying lengths. The chart is typically divided into sections for different dimensions of features. Zero-dimensional features, like connected components. One-dimensional features, like loops. Two-dimensional features like voids, and so on. A whole series of very short bars at the bottom of the chart would represent features that appeared and disappeared almost instantly. This is the noise. These are the random fluctuations and minor details that we want to ignore. They are the topological equivalent of static on a radio channel, fleeting and meaningless. The real story is told by the long bars. A long bar represents a topological feature that was robust across many different scales of analysis. It's a pattern that persisted. For example, a very long bar in the zero-dimensional section indicates a major stable cluster of data points that remained separate from other clusters for a long time before merging. A long bar in the one-dimensional section points to a significant loop in the data, perhaps representing a cyclical process or a recurring pattern of behavior. These long bars are the strong signals, the fundamental architectural elements of our dataset that rise above the background noise. This barcode representation is a powerful bridge between complex mathematics and human intuition. It transforms the abstract output of persistent homology into a simple visual tool that anyone can learn to interpret. We can literally see which features matter just by looking for the longest bars. This allows us to quantify the shape of our data in a way that is both rigorous and accessible. It provides a fingerprint, a unique signature of the data structure that can be used to compare different data sets, track how a system changes over time, or identify anomalies that deviate from the expected shape. Topological data analysis, TDA, is revolutionizing machine learning by making models more robust and data efficient. Traditional models, especially deep neural networks, can be brittle and easily fooled by noisy or unfamiliar data. TDA introduces topological features, capturing the essential shape of data, as new noise-resistant inputs for algorithms. By computing a dataset's barcode, we summarize its structure, providing models with features that are stable, even when the data is distorted. For example, in image recognition, a TDA-enhanced model can recognize a cat by its general shape, not just pixel patterns, making it resilient to changes in pose or background. This approach helps models generalize better, even with smaller or messier datasets. In fields like medicine or finance, where data is scarce and reliability is crucial, TDA's robust features are game-changing. Instead of memorizing every detail, models learn the underlying structure of the forest, not just the trees. By teaching machines to see the shape of data, Topology is building a new generation of more intelligent, reliable AI. The future of machine learning is not just about more data, but about smarter, shape-aware algorithms. Topological data analysis has transformed cancer research by revealing hidden patterns in complex genetic data. In a landmark study, researchers used TDA to analyze breast cancer genomes, mapping relationships between genes rather than just individual mutations. The result was a topological map, a Y-shaped structure, unveiling new subtypes of breast cancer that traditional methods missed. These subgroups had distinct survival outcomes, and crucially, one aggressive group shared a genetic signature linked to an existing drug. This insight, invisible to standard statistics, pointed to new treatment possibilities. TDA turned overwhelming genetic chaos into a clear, actionable map. By seeing the shape of the data, scientists identified patient groups and therapies that were previously hidden. This approach is a powerful example of how topology can lead to real-world, life-saving breakthroughs. Understanding the structure of disease data opens new avenues for targeted therapies. TDA is helping transform cancer research from data overload to new hope for patients. The brain's complexity is staggering, with billions of neurons firing in intricate patterns. Neuroscientists use TDA to analyze high-dimensional brain activity data, searching for meaningful structure in the chaos. In one study, researchers tracked the topological shape of neural responses as subjects viewed images. They found that brain activity forms distinct, fleeting loops and cavities, topological shapes that reflect the complexity of the visual input. Simple images produce simple shapes, complex images, more intricate ones. These shapes are not random. They are part of the brain's code for processing information. TDA reveals that information is encoded not just in neuron firing rates, but in the global geometry of neural activity. This new perspective could lead to better understanding and diagnosis of neurological disorders. By mapping the shape of thought, topology helps decode the brain's secret language. TDA is opening new frontiers in neuroscience, from basic research to clinical applications. Engineering is being transformed by topology optimization, a method that designs materials for maximum strength and minimum weight. Instead of trial and error, algorithms now scope the ideal internal structure for parts like aircraft brackets or medical implants. Engineers define the space and performance goals. The algorithm decides where material is needed, creating organic, efficient shapes. These designs often resemble natural structures: bone, plant stems, spider webs, optimized by evolution for strength and lightness. 3D printing makes it possible to manufacture these complex geometries, once impossible with traditional methods. Companies like Airbus and GE use topology optimization to reduce weight and fuel consumption. In medicine, custom implants mimic bone structure for better integration and durability. Topology is literally reshaping our world, making products smarter and more efficient. The future of design is driven by mathematics, not just intuition. With topology, we're building a world that's lighter, stronger, and more sustainable. Financial fraud hides in vast networks of transactions, often eluding traditional detection methods. TDA gives analysts a new tool, mapping the shape of transaction networks to spot unusual patterns. Legitimate activity forms familiar clusters and hubs, but fraud creates long chains and loops, topological signatures of deception. Persistent homology scans these networks, flagging suspicious shapes like intricate loops or even fraudulent Klein bottles. These patterns are nearly impossible for humans to spot in massive data sets. TDA's approach is more robust than simple rule-based system, which fraudsters can easily evade. By focusing on network structure, TDA uncovers novel and evolving fraud schemes. It provides early warning, helping institutions protect against financial crime. The shape of connectivity reveals what simple statistics cannot. TDA is becoming a critical weapon in the fight for financial security. Drug discovery is a race against time, cost, and complexity. At its core, a problem of molecular shape. TDA offers a breakthrough by describing molecules through their topological signatures, not just atomic details. Scientists compute the barcode of a protein's binding pocket, capturing essential cavities and tunnels. This fingerprint allows rapid screening of millions of drug candidates, filtering for those with matching topological features. The result: faster, cheaper identification of promising compounds. Comparing topological signatures of successful and failed drugs reveals what makes a molecule effective. This knowledge guides the rational design of new optimized drugs. Topology translates the geometry of life into actionable insights for medicine. TDA is accelerating the development of tomorrow's therapies, making drug discovery smarter and more efficient. As we move into an era of increasingly autonomous systems, the principles of topology are becoming essential for teaching robots how to navigate and interact with our complex, unstructured world. The field of robotics is no longer just about programming a mechanical arm to repeat a precise motion in a controlled factory setting. It is about creating machines that can move, perceive, and make decisions in dynamic environments like a busy warehouse, a cluttered home, or even the surface of another planet. For these robots, a purely metric understanding of the world, one based on exact coordinates and distances, is often too rigid and brittle. They need a more flexible, abstract understanding of space, which is precisely what topology provides. Consider the challenge of a robot navigating a building. A traditional map might store the exact coordinates of every wall and obstacle. If a piece of furniture is moved, or a new temporary obstacle, like a box, is placed in a hallway, this entire metric map becomes outdated and potentially useless, causing the robot to become stuck or lost. A topological map, however, captures a more fundamental level of understanding. It represents the environment as a graph of connected spaces and pathways. It knows that the kitchen is connected to the hallway, and the hallway is connected to the living room. It understands the connectivity of the space, not just the precise geometry. This topological approach makes robotic navigation far more robust and adaptable. When an obstacle blocks a specific path, the robot doesn't see its entire world model as invalid. Instead, it understands that one connection in its topological graph is temporarily broken and can easily reason about alternative routes. It can look for another path from the hallway node to the living room node. This is especially crucial for swarm robotics, where groups of simple robots must coordinate their actions. By sharing a common topological map, the swarm can collectively understand the structure of their environment and efficiently divide tasks, like exploring all reachable areas, without needing constant high bandwidth communication about precise locations. Furthermore, topology is helping robots to understand and manipulate objects. For a robot to grasp an unfamiliar object like a coffee mug, it doesn't need to know its exact dimensions. What it needs to understand is its topological structure. It has a main body that can be gripped and a hole, the handle, that it should avoid or use strategically. By analyzing the shape of an object through its sensors and computing its topological features, a robot can develop a more intelligent and flexible grasping strategy. This shift from rigid geometry to flexible topology is a key step in creating robots that are not just automated, but are truly intelligent partners in our world. Beyond the immediate applications in robotics and data analysis, topological thinking is beginning to influence the very architecture of artificial intelligence itself. Researchers are exploring how the principles of connectivity and structure can be used to be more powerful, efficient, and even more interpretable AI system. The goal is to move beyond the current paradigm of massive monolithic neural networks and towards AI that has a more explicit understanding of the shape of the problems it is trying to solve. This involves designing AI models whose internal structure mirrors the topological structure of the data they process, creating a deeper and more fundamental form of learning. One exciting frontier is the analysis of the shape of neural networks themselves. A trained deep learning model is a high-dimensional object with millions of parameters defining a complex function. By applying TDA to the internal states and parameter spaces of these networks, researchers are beginning to understand how they learn. They can visualize the geometric pathways the network takes during training and see how it organizes information into distinct clusters and structures. This provides a new window into the black box of AI, helping us to understand why certain network architectures work better than others, and potentially diagnosing problems or inefficiencies in the learning process. This understanding can then be used to design entirely new types of AI. For example, graph neural networks, or GNNs, are a class of models explicitly designed to work with data that already has a network structure, like social networks or molecular graphs. These models are inherently topological, as their operations are defined by the way information flows along the connections in the graph. The future may see the development of topological neural networks that are even more general, capable of learning and adapting their own internal connectivity to best match the intrinsic shape of any given data set, creating a perfect fusion of model and data structure. Ultimately, this points toward a future where AI does not just process data, but understands its underlying abstract form. This could lead to more generalizable artificial intelligence, systems that can transfer knowledge learned from one domain to another by recognizing that the two problems, while superficially different, share a similar topological structure. It is a profound shift from learning by statistical correlation to learning by structural analogy. By teaching our machines the language of topology, we are not just giving them a new tool, we are giving them a new way to think, one that may be a critical step on the path toward creating truly general and insightful artificial intelligence. Throughout this journey, we have seen how a seemingly abstract branch of mathematics is having a profound and tangible impact on our digital world. From the life-saving discovery of new cancer subtypes to the design of lighter and stronger materials, topology is proving to be a critical tool for navigating the complexity of modern information. It has given us a new lens through which to view data, shifting our focus from simple numerical quantities to the deeper, more fundamental properties of shape and connectivity. This represents more than just a new analytical technique. It signifies a fundamental change in how we approach problem solving in an age of overwhelming data, urging us to look for the forest, not just the individual trees. The recurring theme is the power of abstraction, the realization that a coffee cup and a donut share a common essence. A single whole is the same insight that allows a computer to recognize a recurring cycle in financial data or a robust cluster of patients in a genetic dataset. By learning to ignore the noisy, irrelevant details of precise measurement and focusing instead on the stable, enduring structures, we unlock a more resilient and often more insightful form of understanding. This is the core gift of topology to computer science. It provides a robust language for describing structure in a way that is immune to the chaos and deformation inherent in real-world data. The real-world impact is already significant and continues to grow at a rapid pace. We are building more resilient cybersecurity systems by mapping the shape of network vulnerabilities. We are accelerating drug discovery by matching the topological signatures of molecules and proteins. We are creating smarter robots that can navigate our world by understanding the connectivity of space rather than just memorizing coordinates. In each of these domains, topology is not just an academic exercise. It is the engine driving tangible breakthroughs, making our technology more intelligent, our infrastructure more secure, and our scientific discoveries more profound and impactful. Ultimately, topology encourages us to think in connections, not just in numbers. It reminds us that the most important truths are often not found in the individual data points, but in the relationships between them. As we generate ever more data, this ability to perceive and interpret its underlying shape will become an increasingly vital skill. The secret geometry of information is no longer a secret. It is a map that is guiding the next wave of innovation, shaping a future where we can make sense of complexity and find elegant, simple structures hidden within the noise of our digital age. The world is built on connections, and with topology, we finally have the tools to see them